So for the first lesson of normal distribution, I just want to go through an overview of what it is and how this works. And even though most of this is done by calculator, just one or two things that you still need to be familiar with and know how to do by hand. So let me go through some of the basics for you. But the gist of it is that normal distribution is an ideal scenario whereby data is perfectly distributed. If we were to look at a certain case where, sorry, just trying to get all those up there for you. If we were to look at a certain case where, I was to gather data and I was to figure out all the standard deviations and start analyzing the data, well, it would be meaningless without some sort of standard to compare it to. If you're brand new to the United States and you have never used the A, B, C, D, F system of grading before, and you get a test back and I tell you that that's a B, you would have no idea if that's good or not unless you had some sort of standard to compare it to. So if I were to tell you, well, C is the standard average, well, now you can look at your B and say, oh, well, that's better than the average. It's good. I compared it to the standard. So that's the idea of this too, is it creates the standard setting for. All right, so we're going to be looking at normal distribution in this next unit. For the first lesson, I just want to get you an overview of what normal distribution is and how it works and some of the basic things that you do need to know off the top of your head, even though most of this will be done on the calculator. The main idea, though, for normal distribution is it is a perfect scenario for data that was gathered. In order to analyze data, you need some kind of a standard to compare it to. If you were brand new to the United States and you've never gone through the A, B, C, D, F grading system, and you get a test back and it says B, you would have no idea if that's good or not unless you had a standard to compare it to. So if I were to then tell that person, well, C is the standard average score on a test, well, then they would look at their B and say, oh, then this is a good score because now I've compared it to the standard. And I can see that it's better than the average. So that's the idea behind normal distribution, is it gives you a standard setting. So this is like a ideal perfect case scenario of data. So first things first, some basic properties of what makes normal distribution the standard. We're going to be looking at something called a bell-shaped curve. It is perfectly symmetrical about the mean. So the mean, the mode, and the median all have the same value, and they will be the center of our bell curve. Notice they do use a different symbol here for mean in this unit. We use the X with the bar on top. This is another symbol that is used for mean. So get used to that for the mean. So let me keep going under that. So total area under the curve is 100%. That simply means all the data that we gather is all under the curve. Every single score or data unit that we've observed and gathered, it's all represented underneath the bell curve. So in this perfect setting, the mean would be the center of the curve, and that means I have a perfect split. I get 50% of the data to the left of the mean and 50% of the data to the right of the mean. So that's one of those sets of numbers that you need to be familiar with. Another thing that you need to know is once you establish the mean of the data, the mean goes in the middle of the curve. From there, we branch out with standard deviations. And so if we know the standard deviation, we can move one standard deviation to the right of the mean and one standard deviation to the left of the mean, and from left to right within one standard deviation would contain 68% of all of the data. And I'm going to go through a couple breakdowns here in a second with the graph. So just know these numbers. These are ones that you're going to be expected to know, and you're going to have questions regarding these numbers, so this is important. So if I were to branch out 2 standard deviations from the mean, that would contain 95% of all of my data. And the last one, 3 standard deviations, would contain 99% of all of my data, which means I got 1% left over. So I'm going to have a 0.5% way to the left and a 0.5% way to the right under my curve. So expected values we'll get into when we get to some real examples with numbers. So let me show you a curve. So this is the bell-shaped curve with all the information that I was just talking about, but now you can see how that looks within the graph. So we're going to have a bell-shaped curve, which will come out here better in a second. But again, you got the mean in the middle, You're going to have 50% of your data in that blue shaded area to the left. You'd have another 50% to the right. Came out a little weird. This is supposed to be facing the center, so you get kind of this bell-shaped curve that would do this. So I kind of have to flip that green thing around, but anyway, so you got 50% on either side. This next one comes out a little better. So if I move 1 standard deviation to the left and 1 standard deviation to the right, and I highlight all that area, that would contain 68% of all of the data that we've gathered. And this is, again, under that perfect case scenario. So one thing you need to know about that is remember, this is within 1 standard deviation from the mean, is 68%, which means this piece right here is half of that. So I got 34% right here. I got another 34% right here. So that's 68% within 1 standard deviation. Oftentimes I get the question from students, is that within 1 to the left or to the right? Well, within 1 means left and right. So this entire shaded area is within 1 standard deviation. Any value that's right here is within 1 standard deviation from the mean. Any value over here is within 1 standard deviation from the mean. So this whole thing represents 68%. So here we go. The next number that I threw at you, within 2 standard deviations. So I'm going to go 1 more standard deviation to the left and 1 more to the right. And so now the green area represents 95% of all of my data. We are within 2 standard deviations of the mean total. And then the last one that you need to be familiar with is if I go 1 more standard deviation left and right, you are now containing 99% of all of your data. Is within that blue shaded area. And again, these split in half both directions. So again, from this red line to this blue line is half of 99. So 49.5. And then same thing here. From this red line to this blue line is the other 49.5%, which means I got 0.5% right here. I got another 0.5% right here. So I want to jump over to a drawing that I made. I want to show you something as you really break those down into individual locations. I wanted you to see sort of a better idea of the breakdown of all of those numbers that doesn't come up in the PowerPoint. So remember that I said within 1 standard deviation, so here's the mean. So from this area, if I'm within 1 standard deviation, that's that entire shaded area, it represents 68%. So I'm going to split that in half between 34 and 34. Within 2 standard deviations, so from this guy all the way to this guy, represented 95% of all of my data. And again, you can, if I were to break that in half, that means from right here to right here is half of 95, which is 47.5%. So if from here to here is 47.5, and I already know this is 34, that makes this the remaining 13.5% within that little area right there. So same thing on the other side. And again, from within 3 standard deviations, so from right here to right here, I get 99% of all of my data. So half of 99, right, we know is 49.5. And again, so that means from right here to right here is 49.5. If I subtract out the 2 that I already have, that leaves me with 2% for that little area right here. Same thing on the other side. And again, if this is 99% from right here to right here, I got 1% left. So I'm going to give half of that percent to the far right and half of that percent to the far left. So this is a way of just looking at the breakdown so that you can see how much every section of that curve is worth in terms of percents. So let me take you through 2 examples here so you can see how some of this works within a real problem. So for this one here, we got the wait times for an elevator are normally distributed with a mean of 1.5 minutes and a standard deviation, that should say, of 20 seconds. So first things first, you're not normally going to have to do this, but for this problem, you need common units. You can't do 1 in minutes and 1 in seconds. So instead of doing this as 1.5 minutes, we're going to see that as 90 seconds. throughout the whole problem. So as far as just coming up with the basic sketch of what is taking place here, across the bottom you're going to see the times in seconds. So notice we're going to put the mean right there in the middle at 90 seconds. That was given to us right here. And because we are moving by units of 20 seconds, as you move out from the mean, you're moving in intervals of 20-second intervals. So I'm going to go 1 standard deviation to the left right there at 70. 1 standard deviation to the right is going to be at 110. And then I'm just going to keep moving by 20-second intervals. So here's another standard deviation to the left and to the right, and then one more to the left and to the right. Whenever you sketch one of these curves on your own, you're always going to have 7 numbers. You have the mean in the middle, you got 3 standard deviations to the left, you got 3 standard deviations to the right, so you're always going to have 7 numbers across the x-axis labeled on your graph. And so those are the 7 numbers that you would have labeled on your graph. And this doesn't come up for this sketch for some reason. You'll see it in the next example, but we need to draw the bell curve. This should have a bell curve to it. So I should have a basic bell curve that goes from somewhere in this neighborhood and does something like this, where it curves up, peaks at the mean, and then curves back down on the other side, like the ones that I've drawn for you that you just saw a second ago that I drew. So we should have a bell curve that runs through this. And so that would be the basic sketch, and that's something that you'll be asked to do for certain problems. And now let's take a look at a couple questions that they might ask to follow. So look here at part B. What is the probability, or what is the percent, same thing, that a person waits longer than 2 minutes and 10 seconds for the elevator? Well, again, let's convert this to seconds. So 2 minutes and 10 seconds, we're going to view that as 130 seconds. So what's the probability that they wait more than 130 seconds? So if you would take a look at the graph here, right here at 130 seconds, right, the probability that they wait more than that means I'm looking at the percent from this green line all the way to the right. And if you just keep in mind what I showed you on my drawing, if you just added up the numbers within those areas, based on the drawing that I had just a second ago, you would have 2% for this little area right here. You have another 0.5% out here. So if I just add those up, that's 2.5%. So it's a 2.5% chance that somebody would wait longer than 130 seconds. And so that's something just by adding up the basic numbers that I showed you on the drawing just a second ago. There's more than one way to break down those numbers. Like you're going to see right here, this is their way of looking at it. They said that because 130 was on 2 standard deviations, so I know from this green line to this green line is 95%, which means I got 5% remaining. And if I took half of that 5% to the right and the other half of that 5 to the left, that's the way that we would break it apart. So that gives me 2.5% to the left. That also gives me from here 2.5% to the right. So there's the 2.5% that they're talking about. And you'll see when we go through this in class, this will be shaded for you, so it'll be a little more clear. So 2.5%, and you can write that as a percent or as a decimal. Either way is accepted. Let me show you another one for part C. I should say C, not A. Probability or percent, same thing, that a person waits less than 1:10. So again, we're going to view this in terms of 70 seconds. So take a look right here. If I'm at 70 seconds, so less than 1:10 means I'm going from here to the left. So again, if I just add up the numbers for this section, and this section, that would be the total percent that would answer their question. So again, if you were going to base it off the drawing that I showed you a second ago, that's 13.5 plus 2 plus 0.5. And so if I just add those numbers together, that's a way of getting the answer. And again, you can break down the numbers, view this a little differently at times, but again, that's just an easy way of coming up with those numbers. Most of this you will not be doing by hand. You'll be doing on a calculator, but that will start in our second lesson. We'll start using the calculator. Some of these you run into one or two questions on a test where you need to specifically know what these numbers are in order to get all of the points, and so I want you to be familiar with those, and that's what you'll be using in the first homework assignment. Okay. So one more question right here for this first example. Wait times for an elevator. Again, same information. You got the mean, you got the standard deviation. So change in question. This one now says that 200 people were observed at a length of time for how long they waited for the elevator. And we are now looking for something called the expected number of people that will wait less than 50 seconds for the elevator. This comes with one extra step, but if you don't read carefully, you'll miss it. So we're now looking for an expected number of people. So once we figure out the percent, we have to do the percent of 200 in order to figure out how many people we're talking about here. So this is the one extra step. So first things first, less than 50 seconds. Right here is 50 seconds. So based on what we've talked about so far, that would be 2 plus 0.5, so 2.5%, would be the probability of this happening. So if we said, okay, well, let's take 2.5% of 200, that will tell us how many people we expect to wait less than 50 seconds. And so that's what they're going to show you right here. So they figured out that it was 2.5%. We multiply 0.025 times 200 to figure out how many of those 200 people we expect to wait less than 50 seconds. So my word of warning to you on this is make sure that you read carefully. Oftentimes on a test, people will just give the percent as their answer and they're going to forget to apply it to the 200 to get this number here. So make sure that you understand the difference between whether you're looking for an expected number versus a probability. So last example here for the first lesson, 250 women are normally distributed with a mean of 1.68 meters and a standard deviation of 0.06. So again, the first thing you need to know how to do is do a proper sketch. And so again, you're always going to start by just putting the, by just putting the mean in the middle, and then we're going to move with standard deviations. So right here we have the 1.68 in the middle, and then we're going to move by units of 0.06 to the left and to the right. So from 1.68, if I subtract 0.06, that puts me at 1.62 to the left. But if I were to add 0.06 to 1.68, that puts me at 1.74 to the right. So right there we are within one standard deviation of the mean. Now we're going to be within 2 standard deviations of the mean. And now we are within 3 standard deviations of the mean. So you would have those 7 numbers labeled on your sketch. You would draw a bell curve. There's the bell curve within your graph. And again, typically I label these across the x-axis down here, and that's where you will normally see them as well. So anyway, that's the sketch that we need to be able to come up with. So second question, probability that a woman has a height between 1.56 and 1.74. Again, remember this is a probability question, so we want to answer this with a percent. So one way to figure this out is just to add up the percents that I showed you within my drawing. So from 1.56 to 1.74, I would be adding 13.5 plus 34 plus 34. And that's one way of getting the answer. You're going to see they do it just a little differently. They looked at this and said, well, we know that within 2 standard deviations of the mean is 95%. So half of that, which would go from here to here, would be 47.5. So they figured that from green to red is 47.5, and then we could add the additional 34% right here, and that's the way they kind of pieced it together. But it doesn't really matter. Any way you come up with the total percent is good. So there you go, 81.5% would be our total. Last question, and again, I want you to see the change in question. Notice that part B asks for a probability. Part C is now asking for an expected number. So this comes with one extra step. This said a height greater than 1.5. This is where I would encourage you to maybe pause the video and try this one on your own. But a height greater than 1.8, sorry. So right here is 1.8. So we're trying to figure out what percent would be to the right of 1.8. And then we're going to apply that to the number of women that were tested on this to get our expected number. And so that's where we're going to finish this one off. So we know there's 2.5% to the right of 1.8. And if we did now 2.5% times the 250 women that were tested, we would see that represents a total of 6 women that we would expect to fit this scenario. So again, with the expected number question, you got to take this one extra step of multiplying it by the amount surveyed to get your answer. So the rest of this we'll be doing with a calculator for the rest of the unit, but these are some things that you just need to be familiar with, some things that you'll have to do by hand, some percents that you got to be comfortable with. So the two main things I would say you need to take away from this video is you need to know how to draw a proper sketch and label the proper values along that sketch. The second thing would be to make sure that you know the 4% that we listed on the first page of this PowerPoint. So you need to know that there's 50% to the left and to the right of the mean. You need to know that there is 68% within 1 standard deviation of the mean, 95 within 2, and 99 within 3.